In this video, we're going to begin our section on related rates. So oftentimes we can compute the rate of change of one quantity in terms of the rate of change of another quantity. How we do this is our solution to these types of problems will be to find an equation that relates the variables, and then we're going to use the chain rule to derive both sides of the equations. Once we do that, we're going to get some rates of change with respect to our independent variable or some independent variable within our equation. And if we know those rates of change, then we can just plug that in order to solve for some other part of the equation that we may want to know. So let's get started with just an example of something like this. So here in this example, water runs into a conical tank at the rate of 9 cubic feet per minute. This tank stands point down and has a height of 10 feet and a base of radius 5 feet. How fast is the water level rising when the water is 6 feet deep? Originally, this seems like a complicated problem, but let's write out our variables and draw the picture of what's going on, and that will help reduce what is happening quite a bit. I do suggest that you copy down this question now and pause the video to do that, and then carry on once you've got the problem copied down. All right, let's go ahead and draw our picture now. So we had a conical tank, point facing downward, and we have water that is currently 6 feet deep. So let's draw this here. This is 5 feet. We have a total height of 10 feet. This radius here is x. Our height is a variable that's changing, which is y. And currently that is 6 feet, but we also just want to write the variable y here because that's changing. Anything that's changing is something that we will want to have as a variable. So let's go ahead and write out what's going on here. Our variables are, let's see, capital V is going to be the volume of the water in the tank. And this is in cubic feet at time t. So this is the V is the volume of the water in the tank at time t. All right. And why do we even think that that's going to be useful, right? We were told that the water runs into the conical tank at a rate of 9 cubic feet per minute. So we're talking about a volume of water here. Let's see. We were also asked for how fast is the water level rising when the water is 6 feet deep. Well, we have some variable x here that represents the radius of the surface of the water at time t. And then y is the height of the water at time t. And what we notice is that v, x, and y are differentiable functions of t, so with respect to the time. Okay, so that's what we know so far. And now let's try to plug all of this information into a formula, or at least find an appropriate formula, and then we will derive that. So we can write down some more information that we know. right? We know that we want to find the rate of change of the height when the height is 6 feet. And we also know already the rate of change of the volume. Okay. So the water has volume, and our formula for volume is V is equal to 1/3 pi x squared y. How do we know that? Well, that's just the volume formula for a conical, for a cone. So that's something you could look up if you don't already have it memorized. And to be fair, I do not have it memorized, so it's totally okay to look that up. So here is our volume formula. And we have our variable y in here. We need to know the rate of change of y. So we want the variable y in here. So when we take the derivative, we're going to get that. We also want the variable v in there since we know the rate of change of the volume. So we have found a formula that relates these things, relates the volume and relates the height of the water. And that is this equation. So once we have this equation, we need to do a couple of things. First, we only want 2 of our variables here. We don't know anything about x or dx dt, so we need to eliminate that variable. Well, we can use similar triangles. So let's take a look back at our picture. We can use similar triangles here to notice that if this is some angle theta here, that tangent of theta is equal to opposite over adjacent, so x over y, which on the bigger triangle here, because this is the same angle for that bigger triangle as well, that is equal to opposite 5 over adjacent 10. And so we get this right here. We don't know the angle theta, so we don't actually care about that part. We just need this formula here. So x over y is equal to 5 over 10. Which gives us 10x is equal to 5y, or in other words, x is equal to y over 2. Oh, wow, sorry, I was way off the page. So we had our formula x over y is equal to 5 over 10. This gives us 10x is equal to 5y, which is x is equal to y over 2. So we can replace here now. So this is v is equal to 1/3 pi y over 2 squared times y, which when we square this and reduce everything, we get that v is equal to pi over 12 times y cubed. All right, and now we can take our derivative. We take the derivative with respect to time, right? Our information here is all given in terms of time, dv dt. And we also want to know the rate of change of the height with respect to time. So we're deriving with respect to time. That's what tells us that. So this, take the derivative of the left-hand side, we get dv dt. Take the derivative of the right-hand side. This is the derivative with respect to t of pi over 12 times y cubed. Well, what is that? Well, this is pi over 12 times, now let's take the derivative of y cubed with respect to t. Notice that y is a differentiable function with respect to time, right? We said that already. So the derivative of the outer function is 3y squared, and then times the derivative of the inner function. The derivative of the inner function is just the derivative of y with respect to t, so that is dy dt. So when we reduce that right-hand side, we get dv dt is equal to pi over 4 times y squared times dy dt. Okay, now we can go back and plug in the fact that we knew y was 6 feet. And so since y is equal to 6 feet, we can do, and also, sorry, dv dt was equal to 9. We can go ahead and plug all of this in. So we get 9 is equal to pi over 4 times 6 squared times dy dt. Hey, dy dt is what we're looking for, so we didn't plug anything in for that. This is 36. So 36 over 4 is 9. So this is 9 is equal to 9 pi dy dt. All right. We can divide by 9 pi here, and we get 1 over pi is equal to dy dt, which is approximately 0.32 feet per minute. So this gives us our rate of change with respect to time of the height of the water. All right. And that will conclude this first video on related rates.